Okay, so we're going to do part C of the midterm review, the last part, which is on sets, functions, and sets, functions, sequences. Awesome. Okay, so functions. Let's see. So, or sets, I guess, first. So what's a set? Well, we don't really have a good definition for a set. A set is just like a collection of objects, of things. There's not really a good definition for it. We usually denote sets using these curly brackets. So like we have, say, the set that contains 1, 2, 3, 4. And let's say we have the set that contains 3, 4, 7. Okay. And maybe I'll make one more set. Let's make the set that contains just the number 2. Cool. So I'm going to call this set A. I'm going to call this set B. And I'm going to call this set C. Now someone asked me, what does it mean when you put 2 dots in front of an equal sign? That just means like we're defining a variable. So we're defining the variable A to be this, we're defining the variable B to be this, and we're defining the variable C to be this, right? In computer science, you do something similar. You might do something like int x equals 5 or something. That single equal sign is the same thing as our dot equal sign in math. Whereas like in an if statement, you might do like if x equals 5, right? That double equal sign. We just use a single equal sign for that. So that's the difference here. The colon dot is like assigning a variable or declaring a variable. Cool. Okay, so now let's talk about like some set operations. There are operations that go along with sets. One of them is that we can take intersections and unions. Okay, so what's an intersection? Let's start with that. Intersection. Intersection looks like an upside down U, I guess. Like that. Intersection means you go through each of the 2 sets and you say, okay, it needs to be in this set and it needs to be in this set to be included in the intersection. So the intersection is a set, the output's a set. It's the set of all common things between A and B. So 1 is in A, but it's not in B, so it's not in the intersection. 2 is in A, it's not in B, so it's not in the intersection. 3 is in both, so 3 goes into the intersection. Same thing with 4. 7 is only in B, so it's not in the intersection. Okay, what about if I did A intersect with C? Well, if I do A intersect with C, the only thing that's in common is 2. So it's actually just equal to C. And then another one is, let's do B intersection with C. Well, B intersection with C, they have nothing in common. So we say that the intersection is the empty set. You can either write it using like this circle with a slash through it, or you can write it as like 2 empty curly brackets with nothing inside them. Cool. Okay, so we've got a couple examples here. Let's add some terminology. So this, when we have like a set that just has one thing in it, we call that a singleton. Why do we call it that? I don't know. We're weird. What do we call some of these intersections? So this is just sort of a normal intersection. This one here, where A intersected with C gives me C, or gives me one of the whole sets that we started with. This tells us something. This tells us that that C, I should write it this way better, C is a subset of A. This symbol here means subset. So that means C is like a subset within A. So we have A, C is inside of A. You could pick elements out of A and you could get C, right? And notice like the direction of this arrow, right? So I could say that C is a subset of A, but I couldn't flip this like this symbol backwards. This would be the opposite, that A is fully inside C, which it's not, right? So this is not true. Yeah, so those are called subsets. This is a subset. What about this one, B intersect with C? We say that these two sets are called disjoint. We say that they're disjoint. Why do we say they're disjoint? Because there's nothing in common between B and C. That means they're disjoint. You can almost think of them like Venn diagrams, right? So an intersection normally is like literally the part where the two circles might intersect. This would be the intersection. This might be like A, maybe this is B. And then in here we have the numbers 3 and 4. The subset one looks something like this. Maybe this is A and this is C. So the intersection is just all of C, right? The last case here is where the intersection is, they don't intersect, right? So disjoint. Maybe this is B and this is C. They just don't overlap. Those are the three possibilities. Okay, we've talked about intersections enough. Let's switch gears a little bit here, and we can talk about unions. What's a union? Well, a union, if you think about intersections kind of being like and, in that it has to be in A and it has to be in B, the union's kind of like or. It's like it has to be in A or it has to be in B. So let's write out these unions. A union B, we use like a sort of a smooth looking U to mean union. A union B means it has to be in A or it has to be in B. Okay, well, 1 is in A, 2 is in B, sorry, is in A, 3 is in both, so it's fine, 4 is in both, 7 is in B. So really you're just combining the sets together when you do union, right? Using like sort of your Venn diagram example, the union of these two sets is literally everything, right? Union's just both of them together. What about if we look at subsets? What do we get when we get the union? So if we do A union C, now remember that C is a subset of A. So when we do A union C, we actually just get A, right? I'll let you logic that out, you get A. And if we do the intersection of, so the union of two disjoint sets, we actually just get the two sets put together, right? So you could literally just do, well, you know, 2, 3, 4, 7, like that. And again, in this case, if we look at the Venn diagrams, this would be B union C. A union C would look like this. It's taking all of it. And of course, I showed you A union B before. Hopefully that makes sense. That's unions. We have a couple other operations that we can do with sets. First one is kind of like not, the equivalent of not in sets. So the not operator, we call it the, what do you call it? I'm blanking on the word. Wow. Just like on the tip of my tongue. I'll let you look it up because I don't want to pause the video. The way you write it, you put a bar over it. So a bar is the same thing as the set of all things that are not in A. Does that make sense? It's the set of things that are not in A. Okay, well, let's give an example. Let's say that E is defined to be the set of all even numbers. Then E bar is the set of all odd numbers. So if a number is not even, then it's odd. Right? Yeah. Okay, so we've got that. Then what are we gonna do then? Let's talk about set subtraction. So you can subtract sets. So let's say that I have, here I have A, well we said that C was a subset of A. I can do I can do A minus C, and we usually do like a minus with like a down slash. Sometimes you just see it as literally a minus sign, but I usually do like a slash. So A minus C. In this case, we're gonna take the things in C and subtract them, drop them from the list A. So if we get rid of the thing in C, which is 2, all we're left with is 1, 3, 4. What about if we do, let's do A minus B. So A minus B, what do we get? We get 1 and 2, since the 3 and 4 are gonna get dropped. What about if we did, let's see, we do B minus A. Well, B minus A, the 3 and the 4 are gonna get dropped. All we're left with is 7. So A minus B is not the same thing as B minus A. Be careful with that. Cool, okay, there's another operation with set subtraction. I got the word for this thing, this E bar, it's called the conjugate. It's right on the tip of my tongue. It's called the conjugate. So hopefully that makes sense. Cool. Let's do one last example, or one last thing here. We have something called the direct product of sets. What's the direct product? The direct product is like, it looks like this, A times B. So you can multiply sets together. How do we do that? Well, what you do is you take every pair of possible things, where you take one thing from A and one thing from B. So what's it gonna look like in this specific case? Well, it's gonna be, usually what I like to do is I like to pick something in A and then pair it with everything in B. So we're gonna pick 1, and then we'll say, well, 1 goes with 3, 1 with 4, 1 with 7. And I often will just put them on new lines. You don't have to. I just find it a little bit easier. Now we've done 1 with everything in B, now let's do 2. 2 with 3, 2 with 4, and 2 with 7. Now we can do 3 in A. So we get 3 with 3, 3 with 4, 3 with 7, and 4s. 4 with 3, 4 with 4, 4 with 7. That's the direct product. It's pairs. It's a set of pairs, of tuples, right? Hopefully that makes sense. That's our direct product. I think that's it for sets that I really want to go through. There's a bunch of identities you can look up, and I implore you to do that. Yeah, that's pretty much it for sets. At least that I can think of. Should be able to do proofs with sets too. Okay, maybe a good example, just to give you one you can practice, is let's say prove the formula for A intersection with B conjugate. See what that equals. It's actually going to be De Morgan's law. So yeah, you'll find out that it's De Morgan's law. It's just going to be, sorry, not B, A, actually doesn't matter, but A bar union B bar. I want you to prove that. So prove that. That's a good proof. Okay. So from here, let's talk about functions. What is a function? A function is just a set of tuples. Huh? Yeah, it's a set of tuples. So where it's a set where you have the input as the first thing and the output as the second thing inside of a pair, inside of round brackets like that. It's almost like x, y. That's what a function is. Function is a set like that. Although we usually don't write it like that. We usually write it something maybe like this. What are these R's and Z's? We have some specialized sets, and I'll write them out here. So we have R, which are the real numbers. We have Q, which are the quotients. We have Z, which are the integers. And we have N, which are the natural numbers. So like the counting numbers. Cool, there's more. You don't need to know them. So we have this function. It goes from one input, set of all possible inputs, which we call the domain, to a set of all possible outputs, which we call the codomain. Not comain, codomain. Cool. Yeah, that's what that is. And I just gave an example here. And then usually they'll tell you what the function does. So maybe in this case, is going to do, I don't know, floor of X, comma, ceiling of Y. That's a function. Goes from two real numbers to two integers, and it takes the floor of the first one and the ceiling of the other one. What's floor and ceiling? Floor means you round down, ceiling means you round up. Be careful with negatives, because the floor of -1.5, for example, is -2, because you're rounding down. So it's going to get more negative. So I just need to grab a drink here. Hopefully that makes sense. Okay, let's keep going. All right, so we've done that. Next thing is, let's talk about types of functions. So there's sort of two key things that we often ask people to look for. The first one is one-to-one, showing that a function is one-to-one. The second one is showing that a function is onto. What does this mean? Well, one-to-one means that if you give me two outputs of the function that are actually equal, so if f of x equals f of y, if you want to prove a function is one-to-one, you have to show that x equals y for every possible x and y. If the function applied to them are the same, that the inputs have to be the same. In other words, you can't have two different inputs give you the same output. Onto, and also I should write, we have some like special words for these. We call one-to-one injective, and we call onto surjective. Cool. So how do you show a function is onto? Well, onto is usually a little bit harder, but to show a function is onto, what you want to do is you want to show that no matter what, if I give you an output of the function, no matter what, it has an input, at least one input that it came from. So there's no outputs or possible outputs that you can't actually get. An example of a function that's not onto is x squared. So you might be wondering, what do I mean? Well, is there any, x squared looks like this, right? If I were to sort of, maybe I'll draw it here, looks something like this. There's no, well, there are some numbers that you can't actually get. So there's no, if I told you that f of x was equal to -1, well, that's not possible because you can't get -1 out of this function as long as we're going from the real numbers to the real numbers. There's real numbers like -1 that I can't actually get with this function. That means it's not onto. So for it to be onto, you have to have, no matter what output you give me, from in this case r, every single output has to have some possible input that can give it. Could have multiple, but it needs to have at least one. How do we show it? Often what we do is we show that, if you can show that there's one output, if one gets outputted, like the number 1 as a possible output to the function, from there, try and show that you can hit every other possible output using that. Hopefully that makes sense. They are tricky, right? They're more difficult, but you'd have to do proofs for them. You have to show that a certain function is injective or surjective or one-to-one or onto. Yeah, that's pretty much it for functions. And sequences are just a type of function. Sequences, so you have some sequence. Let's say that we have a sequence that looks like this, where it's like S1, S2, off to infinity, right? So you have infinitely many things. Some sequence of numbers. Well, and maybe let's say, for example, we have a sequence that's like, usually you denote it something like this. 1, 2, 3, 4. Very basic sequence. Okay, so in this case, maybe actually I'll change it just to, let's say it's 1, -2, pi, something, right? Say it's that. They don't have to follow a pattern, they usually do, but they don't have to. Okay, so in this case, a sequence is actually just a function. So I'm gonna call this function S. It maps the natural numbers, in this case, to real numbers. So sequences are functions where natural numbers are the domain. So in this case, S of 3 equals pi, right? Third thing is pi, boom. We don't usually write them like this though. We usually write them like S3 equals pi. And the function itself is Sn instead of S of n in brackets. Hopefully that makes sense. That's most of what we covered, at least in tutorials. There might be some extra stuff that Mihai did in lectures that you can look through the notes. But hopefully this gives you a good solid grasp of where you're going with this midterm. So hopefully you can make some use out of this. If you have any questions, of course, send me an email. I'll write out my email address again so that you have it. .ca or .net, either doesn't matter. All goes to the same place for me. So benjamin.fedorik@ontariotechu.ca. You can find it on my website as well. Yeah, hopefully that makes sense. If you have any questions, please reach out. I'm more than happy to answer. Good luck on the midterm, and we'll see you next class if you're taking my class. See you later.